Guys, just have a look at this question. In this question, there are two cases. In case 1, there is a disk of mass m and radius r that is welded at one of the end of this rod, which is massless, and the length of the rod is L. Now, this rod is hinged from the other end and it is free to rotate about an axis which is passing through the hinge. Now, in the second case, this disk is free to rotate about an axis which is passing through the pin, which means that rod is pinned at the center of the disc. So disc can rotate about this pin, as well as this rod is also hinged from the other end, and the length of the rod is same, and rod is again massless. Now rod can rotate freely about an axis which is passing through the hinge in both of the cases. And can you guess the total moment of inertia of the disk in these two systems? Most of you would answer this question very wrong, because you do not know the real significance of parallel axis theorem. And I would tell you the exact mathematical derivation of the parallel axis theorem, which you already know, and the main thing, which is the real significance of parallel axis theorem, in this video. And I would tell you that using the parallel axis theorem denotes there are two motions which are going on in this case. So I would also explain these two motions, and I would explain the real meaning of parallel axis theorem in this video. So without wasting any time, let us start this video. So this is the parallel axis theorem, which says that the moment of inertia of a system about an axis which is not passing through the center of mass, but that axis is parallel to one of the axes which is passing through the center of mass. So the moment of inertia of this system about this axis AB, which is not passing through the center of mass, but this axis AB is parallel to one of the axes which is passing through the center of mass. So the moment of inertia about this axis AB would be equal to the ICOM, which is the moment of inertia about this axis which is passing through the center of mass, plus the value which is m into d square, where m is the mass of the system and d is the distance between these two parallel axes. So this is very important, that moment of inertia, that parallel axis theorem tells us about the moment of inertia of the system about such an axis which is not passing through the center of mass, but that axis is parallel to one of the axes which is passing through the center of mass. Now what is the proof of parallel axis theorem? So to prove this parallel axis theorem, let us consider a system which has n number of masses, and this is m1, m2, m3, m4, and there are n number of masses. Now this is the center of mass of the system, and this is the axis which is passing through the center of mass of the system. And this axis is obviously passing through the system, or it is not passing through the system. It doesn't matter. But what matters is the fact that this axis is parallel to the COM axis, and this axis is separated by a distance of d from COM axis. Now we have to find out the moment of inertia of this system about this axis. So first of all, let us write down the individual formulae for the moment of inertia of these masses about that red axis. So I1 is the moment of inertia for the first mass m1, and you can see the distance of first mass from this axis is r1 plus d. So this is m1 into r1 plus d whole square. Now I2 is for mass m2, and its distance would be d minus r2. So this is d minus r2 whole square. Now the I3 would be m3 into r3 plus d whole square, and I4 would be m4 into d minus r4 whole square. So similarly, if we add up all of these, so the total moment of inertia I would be equal to m1 r1 square plus m2 r2 square up to mn rn square. plus m1 plus m2 up to mn into d square plus m1 r1 d plus minus m2 r2 d plus minus. Why I'm writing this plus minus is due to the fact that it is not necessary that mass 1 is on this side only. It can be at this side also. So I'm writing it arbitrarily and considering that any mass can be on any side of the center of mass axis. So this is m2 r2 into d, and this is up to, this one is m3, this is up to mn rn into d. So taking out this d as common, so we know we know that if we take out this d as common, so the sum of mass movement of a system about of the masses of a system about their COM is equal to 0. So this is m1 into plus minus m1 r1 plus minus m2 r2 plus minus m3 r3 up to mn rn would be 0. So this is the sum of mass moments, and this would be 0 about center of mass. So the remaining terms would be m1 r1 square. In fact, this is m2 r2 square and up to mn rn square plus m1 plus m2 up to mn into d square. Now you can see that this term is the moment of inertia of the system about center of mass axis, plus this term is m system into d square. So this is the parallel axis theorem. Now let us see that why do we write this parallel axis theorem and what is the physical significance of this parallel axis theorem. To understand this, we are considering a rod which is massless. I'm writing it as massless. And there is a ring which has some mass m and radius r. Now this ring is welded at this point. This is welded, and the distance between the center of the disc, center of the ring, and this hinge point is d. So if we are rotating this complete system about this axis, which is passing through this point and which is also perpendicular to the plane containing this board, so this after half rotation, this ring would be at this point, and after another half rotation, this ring would be at this point. Now you can see that in a simple rotation of a disc of a ring, let us write that this ring is rotating about an axis which is passing through its center of mass, and this is point P and this is point S. Now after half rotation about COM, you can see that point S and point P will interchange. There will be S and there will be point P, this is O, and after another half rotation, these points will again regain their original position. So this is now P and this is now S. So you can see that when this ring is rotating about the center of mass axis, then how these points are getting interchanged. So now in this case, you can see that after half rotation, the point S initially was on the right side of the O and P was on the left side. Now after half rotation, now this point P is on the right side of the point O, and point S is on the left side of the point O. Now, even after the second half rotation, these points have regained their original positions. So you can see that in the case in which this ring was rotating about the center of mass axis, then you can see that the moment of inertia about this axis would be ICOM only, and this the center of this ring was at rest. But in this case, the ring when it is rotating about some other axis which is passing through some other point and which is parallel to the center of mass axis, then this ring is in fact also rotating about its center of mass, and its center of mass is also moving around this axis. So there are two motions of the ring, and we have to write down the two moment of inertias. So I total would be the sum of I of rotational motion about COM as well as I revolutional motion of COM about the other axis. So I total would be, this would be ICOM, and this would be md square, considering the ring as a point mass which is concentrated at its center of mass containing a mass m, and the distance of this point mass from this axis is d. So its moment of inertia would be md square. So when a system is rotating about an axis which is not passing through the center of mass, but that axis is parallel to the axis which is passing through the center of mass, then that system is performing two motions. The first motion is the motion of rotational motion, and that rotational motion is about center of mass of the system, as well as the second motion is of the revolutional motion, and that revolutional motion is of the center of mass about some other axis. So the total moment of inertia would be the sum of these two moment of inertias, and hence we write the total moment of inertia as ICOM plus md square. So what the parallel axis theorem tells us that when this system is rotating about an axis which is not passing through the center of mass, then it is performing two motions, and hence we have to write down both the moment of inertias which signifies both the motions. Now some examples of application of parallel axis theorem. So in the first case, you can see that there is a disk, and this disk has an axis which is passing through its periphery. Now we have to find out the moment of inertia about this axis, and we already know the moment of inertia about its center of mass. So we can write down that I is equal to ICOM plus mr square, where r is the distance between these two axes. So I would be equal to ICOM. ICOM is mr square upon 2 plus mr square. So the moment of inertia of this disk about this axis is equal to 3 by 2 mr square. Now in the second case, there is a rod, and we have to find out the moment of inertia of this rod about this axis. We know that the moment of inertia of the rod about center of mass is ml square by 12. So we can write that I is equal to ICOM plus md square. Now I is equal to ICOM, which is ml square by 12 plus m, and d is the distance between these two axes, which is equal to L by 2. So this is ml square by 4. So the moment of inertia of this rod about this axis, which is passing through its corner, is ml square by 3. Now for the solid sphere, you can see that the moment of inertia about this axis is, let's suppose, I, and about this axis is ICOM. So I is equal to ICOM plus m, this distance is r, so mr square. So I is equal to ICOM is 2 by 5 mr square plus this is mr square. So I is equal to 7 by 5 mr square. So now let's move on some of the questions which are based on parallel axis theorem. There are four spheres, each of mass m and radius r. They are placed in such a way such that their centers are spaced equally at a distance of 3r, making a square. And we have to find out the moment of inertia of this system about these axes. This is the axis number 1, this is the axis number 2, and this is the axis number 3. So we have to find out the moment of inertia of these spheres about these axes. So let us first of all name the spheres. So this is sphere number 1, this is, or we can say that it is A, this is B, this is C, and this is D. So the moment of inertia of the system about axis number 1 would be twice of 2 by 5 mr square. This is the moment of inertia of a sphere D and B because the axis 1 is passing through their centers. Now the moment of inertia of A and C would be equal, therefore it would be twice of m 2 by 5 mr square plus. Now we have already located that this axis is parallel to axis number 1 and this is also passing through sphere A. So the moment of inertia of a sphere A about this axis 1 would be ICOM plus m into this distance d square. And we know that this distance d is equal to a by root 2. So this is m into a by root 2 whole square. Okay, so I1 is equal to 4 by 5 mr square plus 4 by 5 mr square plus m into this is d, d is a by root 2, where a is the side of the square. So side of this square is 3r, so this is 3r by root 2. So this would be m into 9r square by 2, and it is also multiplied by 2. So the moment of inertia of this system about this axis 1 would be 8 by 5 mr square plus 9 mr square. So this is 53 by 5 mr square. This is the moment of inertia of this system about the axis 1. So now let's find out the moment of inertia about axis 3. So about axis 3, you can see that all the spheres are equidistant from this axis 3, and the distance of any one of them from this axis 3, the distance of center of any one of them from this axis 3 is d, where d is 3r by root 2. So the moment of inertia of the complete system about this axis 3 would be 4 times of the moment of inertia of any one of them. And the moment of inertia, let's suppose for sphere A, would be m r 2 by 5 mr square, which is the moment of inertia about its central axis plus the distance md square. So I3 would be 4 times of 2 by 5 mr square plus m into d, which is a by root 2. So this is a square by 2, and A is the side of the square, therefore side of the square is 3r. So A is equal to this distance D is equal to 3r by root. So this is 9r by 2. So I3 is equal to, this is 8 by 5 mr square plus this is 18 mr square. Okay, so 8 by 5 mr square plus 18 mr square will be equal to 98 by 5 mr square. So this is the moment of inertia of this system about the axis 3. Now let's find out the moment of inertia of the system about this axis 2, this axis. So this is the moment of inertia about this axis 2 would be twice of 2 by 5 mr square. So this is the moment of inertia for a sphere B and C, because this axis is passing through sphere B and C, and this axis is also containing their centers. So the moment of inertia of these spheres about this axis would be 2 by 5 mr square. So the moment of inertia of other two spheres would be twice of 2 by 5 mr square plus, now the distance between the axis which is passing through the center of these spheres, and this axis is also parallel to this axis. Now the distance between these two axes is 3r, so this would be m into 3r whole square. So I2 would be 4 by 5 mr square plus 4 by 5 mr square plus this is 9 into 2, 18 mr square. So I2 would be 8 by 5 mr square plus 18 mr square. So I2 would be 98 by 5 mr square. So this is the moment of inertia of this system about the given axis. Now let's move on the next question. In this question, there is a thin rod of total length 4L and total mass 4m, which is bent in a form which is shown in the figure, and we have to find out the moment of inertia of this rod about an axis which is passing through point O, and it is also perpendicular to the plane, this axis. So we can see that the moment of inertia, let's suppose this rod, this part of the rod, this one is A. Okay. Now the second part is B, this is the third part, and this is the fourth part. So the moment of inertia of rod A and rod D will be equal. So I of A will be equal to I of D, and I of B will be equal to I of C. In fact, the moment of inertia of B and C would be 2 by 3 m L square, because in fact 1 by 3 ml square because this axis is passing through any one end of this rod, therefore its moment of inertia would be ml square by 3. Okay, now the moment of inertia of A and D can be calculated by parallel axis theorem. We know that this axis is perpendicular to the rod and it is passing through the center of mass, and this axis is at a distance of, this distance is root 5L by 2. You can find out this distance by using Pythagoras theorem, that this is L and this is L by 2. So this distance would be root 5L by 2. So IA or ID would be equal to ml square by 12 is the moment of inertia about COM axis plus m into
5L square by 4. So taking LCM as 12, so this is ml square plus 15 ml square. So this is 16 ml square by 12. So IA or ID is equal to 4 ml square by 3. Now the total moment of inertia would be IA plus ID plus IB plus IC. So this is twice of IA and this is twice of IB. So I will be equal to twice of IA is 4 by 3 ml square plus twice of IB is 1 by 3 ml square. So I total will be 8 by 3 ml square plus 2 by 3 ml square. So this is the total moment of inertia. So this is 10 by 3 ml square. So the correct answer will be option number B. So this was a complete package of a numerical for parallel axis theorem, and we would be discussing perpendicular axis theorem in the next video and many more concepts which are related to moment of inertia. Thank you.